Okay, in the last video we talked about the definite integral. The definite integral of a function from from a to b is defined as the limit of a Riemann sum. Okay, and so I was going to show you some examples now of us computing definite integrals using the limit definition. Okay, limit of a Riemann sum. Well, so here's an example. Suppose that we want to find the integral going from -2 to 1 of 2x dx. -2 is my lower limit of integration. 1 is my upper limit of integration. Okay, and in general, a is always going to be the smaller number. Okay, when you compare a and b. So I've got a picture of y equal 2x, and I've also represented this from when x is going from -2 to 1. Okay, and we'd like to find the limit as n approaches infinity of a Riemann sum. For this problem, when we work with right endpoints. Okay, so I'm going to draw n rectangles where the right endpoints are touching this line. Okay. The width of each rectangle, delta x, is where we take b minus a divided by n. A is -2, b is 1, so 1 minus -2 divided by n, that'd be 3 over n. By the way, delta x will always be a positive. Since you're talking about the width of a rectangle, that can never be a negative. That doesn't make any sense. So like in this problem, if I were to draw 6 rectangles, let's say, the width of each one would be 1/2. Okay, if I were to draw 12 rectangles, the width of each rectangle then would be 1/4, etc. Okay. X sub 0 is your start point, which for us is -2. And x sub 1 would be where the first right endpoint touches the line. Okay, so that's going to be at 1 increment of the width away from -2. -2 plus the width is 3 over n. X sub 2 would be where the next right endpoint touches the line. That's going to be at 2 increments of the width away from -2. So -2 plus 2 times 3 over n. X sub 3 would be the third right endpoint. That's going to be at 3 increments of the width away from -2, etc. Okay, so x sub I, the ith right endpoint, is going to be at I increments of the width away from -2 from this pattern that we see here. Now, this calculation tells me where the right endpoints would occur if I plug these numbers into the function. Okay, so let's go ahead and begin computing the value of the integral going from -2 to 1 of 2x dx. Well, that's by definition the limit of a Riemann sum. Okay, so the limit as n approaches infinity of r sub n or L sub n, it doesn't matter. Okay, both will produce the same answer here. Okay, no matter how you look at it. So I'm using right endpoints in this problem. Okay, now the area of a rectangle is length times width. The width is 3 over n, and the height of the rectangle would be where I plug in the ith right endpoint into the function. The function f of x equal 2x is inside my integral, so f of x sub I would be -2 times -2 plus I times 3 over n. You're plugging that into the function. Okay, and now we want to find this limit. So let's see here. 2 is a constant, and you can pull constants out of the summation notation. Also, I can split the sum into 2 sums if I want. Okay, so this 2 can come in front. The summation is I equal 1 to n of -2. That'd be -2 times n. All right, remember when you're summing up a constant, n times is just n times the constant. And then plus 3 over n, that's a constant that can come out of my second sum. The sum is I equal 1 to n of I. That's n times n plus 1 over 2. Okay, and be sure that you remove the summation notation. And let's see, if I distribute 6 over n. You're going to have negative 12 from that first part. These n's will cancel. Let's see, 18 divided by 2 is 9. And then you're going to have n plus 1 over n. That's the same as 1 plus 1 over n. The limit is n approach infinity of 1 over n. That's 0. Limit of a constant is always the constant. Negative 12 plus 9 times 1 is negative 12 plus 9 is negative 3. Okay, negative 3 would be the value of this definite integral then. Okay. Now, a couple of notes here. First of all, this is how the calculation would look if I were to use left endpoints. The only adjustment is that where we had I, we're going to replace that with I minus 1, since you're just going to simply back up 1 unit if you're working with left endpoints. You're going to back up one increment of the width on every single one of them. Okay, and here's another note. If f is continuous and non-negative on the interval a to b, then the area of the region bounded by f, the x-axis, and the lines x equal a and x equal b is this definite integral going from a to b of f of x dx. Okay, now the curve being non-negative means that the curve has to lie above the x-axis completely on this interval. This curve did not do that. Okay, if I'm on the interval negative 2 to 1, the curve is not entirely above the x-axis. So my answer, being a negative, makes no sense in terms of area. Okay, like I didn't compute any area here. Now, of course, if I wanted to find a total area, you know, I'm just working with triangles. Area of a triangle is 1/2 base times height. Okay, so that wouldn't be a difficult thing to do here. But in other words, this problem is really just a computational exercise. It has no practical meaning in terms of area. Okay, and I think I've summarized that here. So in the last example, f was negative, from negative 2 to 0, explaining why our answer makes no sense in terms of area. Of course, in this example, one of the things that I would like you guys to pay attention to when you're working with limit of a Riemann sum and definite integrals is if you get a negative, you know, take a look at your problem there and make sure that that is reasonable. Okay, we can probably know early on in a lot of these problems if we end up getting a negative and if that would make sense or not. So, okay, let's take a look at another example. Suppose that I want to find the integral going from 1 to 2 of negative 2x plus 7 dx. Okay, well here's the function f of x equal negative 2x plus 7. That'd be a line, right, with a slope of negative 2. I'm going to pass through the y-axis at 0, 7. And my conditions on x is going from 1 to 2. And so I've marked that enclosed region there. That would be a trapezoid, by the way. And so in this problem, I'll be able to check my answer by just computing the area of a trapezoid at the end. Many times you won't be able to check your answer using just simple geometry formulas, okay? But some, you know, we can do that here. Now, I'm going to use limit of a Riemann sum, and I'm going to choose left endpoints for this problem. Again, it's not going to matter if you choose left endpoints or right endpoints, okay? Just pick one option out of those two and roll with that. The width of each rectangle is delta x. B minus a over n, so 2 minus 1 divided by n, that'd be 1 over n. Okay, and that would be just the general formula for finding the width of n rectangles. So if I draw 4 rectangles, the width of each rectangle would be 1/4. Okay, if I draw n rectangles, the width of each one would be 1 over n. I'm using left endpoints, and so I've drawn a couple of rectangles there where the left endpoint is touching the curve. X sub 0 is always your a value, which for us is 1. X sub 1 is going to be the first left endpoint, which is also when x is 1. In the case of left endpoints, x sub 0 and x sub 1 will always be the same, okay, since your left endpoint is also going to be at your start point. That will always happen. X sub 2 would be where the next left endpoint occurs, and that's going to be one increment of the width away from 1. So 1 plus 1 over n. x sub 3 would be where the next left endpoint occurs, and that's going to be at 2 increments of the width away from 1, etc. X sub I would be where you're starting at 1, and you're going to be at I minus 1 increments of the width away from 1. Okay, or at least that's what we see in the pattern when we compare this multiplier to the subscript is 1 less each time. Now, when I compute this definite integral, I'm computing it as the limit as n approaches infinity of L sub n, limit of a Riemann sum, and so I'll have the limit as n approaches infinity of the summation as I equal 1 to n of the length times the width. The width of each one of these rectangles is 1 over n. The height would be where I plug in the ith left endpoint into the function. Here's the function inside the integral there. And so where I see x, I'm just going to replace that with 1 plus I minus 1 over n. And so that's what I've done in the next line here. I've replaced x with 1 plus I minus 1 over n. 1 over n is a constant that can come out of my sum. Now, of course, the limit is in terms of n, so I can't bring that outside of my limit. Okay, be careful about that. But let's go ahead and split this sum into what would be 2 sums. And you can also then, or it's actually going to be more than 2 sums, it would be 3 sums. And then you can apply your summation, your special summation formulas there. So, okay, I'm going to have negative 2 plus 7 is 5. And when I distribute the negative 2 into this part, it's going to be minus 2 over n times I minus 1. You can then also distribute the negative 2 over n into these 2 terms here, and that's what I've done in the next line. So then I can split this sum into what would be 3 sums. When you're summing up a constant n times, it's the constant times n, or 5n. Minus 2 over n, that's a constant, times the sum as I equal 1 to n of I, that's n times n plus 1 over 2, plus 2 over n, that's a constant. When you're summing up a constant n times, it's n times the constant. Okay, these n's will cancel there. And also, let me distribute the 1 over n into these terms. So you're going to have 5 minus, these n's will cancel, the 2's will cancel, n plus 1 over n, that's the same as 1 plus 1 over n. And then I've got 2 here because these n's cancel, but you're going to bring in the 1 over n, so 2 over n will be at the end. Limit as n approaches infinity of 1 over n, that's 0. Limit as n approaches infinity of 2 over n, that's 0. 5 minus 1 is 4. Okay, so the answer is 4. Now, I can check that. I've got a trapezoid, and so using some geometry here, the formula for the area of a trapezoid is where you take half the height times the sum of the 2 bases. Now, in this problem, you'd have to tilt your head 90 degrees, and we want half the height is 1, times the sum of the bases. So the upper base would have a measure of 3 units. The bottom base would have a measure of 5 units. Okay, 3 plus 5 is 8. Half of 8 is 4. So yeah, that's what I got. Okay. Here's how the formula would look if you were to use right endpoints, and you would still get the same answer if everything was done correctly. By the way, right endpoints is usually going to be our preferred option, since with left endpoints, I've mentioned now a couple times, where you see I, you'd have to replace that with an I minus 1. Now, that wasn't a drastically difficult thing to do here, but in the case of, like, if you have powers or square roots or something like that, it might be easier just to use I rather than I minus 1, okay, to avoid like a foiling out situation or, something like that. But either way would be fine because you still get the same answer when all is said and done. Okay. Let me take a look at another one here. So suppose that we want to find the integral going from -2 to 2 of 4 minus x squared dx. So that would be a parabola. I've drawn the picture. And now this parabola is symmetric to the y-axis. And so I'm going to use some symmetry here in the calculation. You don't need to do that, but it's going to be easier to have this lower bound be at 0 rather than -2. Okay, if I find the area under the curve going from 0 to 2, and then whatever that is, I'll just double that result, I'll end up getting the total area that is under the curve going from -2 to 2. Okay. Again, you don't need to use symmetry, but it's it's convenient to have a bound of 0 rather than some other number there. The width of each rectangle is b minus a over n. B is 2, a is negative. So excuse me, I'm using symmetry here. So b is 2, a is 0. 2 minus 0 over n would be 2 over n. Okay, and x sub 0 is 0. Okay, x sub 1 is where the first right endpoint touches the curve. I'm using right endpoints here, I've indicated that. And that's going to be at 1 increment of the width away from 0. X sub 2, the next right endpoint, would be at 2 increments of the width away from 0, etc. The ith right endpoint would be at I increments of the width away from 0. By the way, it's a good idea to, write out a pattern so you can see where this expression in terms of I is coming from. You don't need to do that, but it's helpful, okay? Now, I've set up my limit here. I've got 2 times the limit as n approaches infinity of r sub n. I'm using red endpoints, which is 2 times the limit as n approaches infinity of the summation as I equal 1 to n of the width times the length. The width of each rectangle is 2 over n. The height of each rectangle would be where I plug in the ith value to get the ith right endpoint there. Okay, so, and it's a good idea to check and make sure that your formula is correct. Like if I let I be 1, the first right endpoint would be at 1 increment of the width away from 0. Well, yeah, that's what I said. Okay, if I is 2, you're going to be at 2 times 2 over n. That'd be 2 increments of the width away from 0. Yeah, that's what I see. Okay, etc. If I plug in n, the n's are going to cancel there, and I'd have f of 2. Okay, well 2 is where I'm ending, right, this enclosed region, and 2 would also be where the last right endpoint would occur. So I know I've got all the rectangles there in this setup. Okay, f of x is 4 minus x squared, so where I see x, I'm going to go ahead and replace that with 2I over n, and then I begin simplifying this. You can, let's see, I guess I brought in the 2. If I didn't do that, I'd probably forget about that being out there. So 2 times 2 over n is 4 over n. And you can then split this sum into 2 sums and use your special summation formulas. If you're summing up a constant n times, that's n times the constant. Okay, minus 4 over n squared, that's a constant, times the sum is I equal 1 to n of I squared, that's n times n plus 1 times 2n plus 1 all over 6. Okay, and if I then distribute 4 over n into these terms, the n's will cancel there. 4 times 4 is 16. And then here's 4 over n times, let's see, 4 times 4 is 16 divided by 6. That would reduce to 8 over 3. You're going to have this n can cancel with this n right here. You'll still have an n squared, which you can put one n underneath the n plus 1, the other underneath the 2n plus 1. N plus 1 over n, that's the same as 1 plus 1 over n. 2n plus 1, that's the same as 2 plus 1 over n. And limit of a constant is always the constant. Limit as n approaches infinity of 1 over n, that's 0. So you're going to have 16 minus 8 thirds times 1 times 2, which gives you 32 thirds as the answer. Okay, and if you wanted to go with left endpoints on this, that would be fine. You would still get 32 thirds, okay, as the value of this integral. Here'd be the setup that you would use. Again, all you're doing is you're replacing I what it was previously with I minus 1, okay, in the case of left endpoints.